Sealtight cannot be used to protect a solid number 4 grounding electrode conductor because it is not considered watertight. A grounding electrode conductor is required to be protected from the elements, and Sealtight, in this specific application, does not provide adequate protection according to code requirements. However, Sealtight is often used for outdoor equipment hookups because it offers flexibility and ease of installation. Furthermore, in those applications, it's designed to be watertight, which is essential for safeguarding electrical connections from exposure to the elements. Regarding grounding U for ground clamps, these are installed with accessibility in mind to facilitate inspection and testing procedures. The National Electrical Code mandates that ground rods and their associated clamps be buried. This burial serves to protect these components from potential physical damage, ensuring their long-term integrity and effectiveness. Ground rods are intentionally buried to establish a low resistance pathway to the earth ground. The resistance value of a ground rod is influenced by several factors. Firstly, the length of the rod plays a significant role. Secondly, the diameter of the rod also contributes to the resistance. Thirdly, the type of soil in which the rod is installed has a substantial impact on the resistance achieved. The National Electrical Code, or NEC, contains specific requirements regarding the installation and protection of grounding electrode conductors, or GECs, and grounding electrodes. These requirements are in place to ensure the safety and effectiveness of the grounding system. A grounding electrode conductor connects the equipment grounding system to the grounding electrode, which is typically a ground rod, ground plate, or other approved grounding means. The purpose of the grounding electrode is to provide a lower impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protection devices such as circuit breakers or fuses. Section 250.64 B of the NEC addresses the protection of grounding electrode conductors. This section states that a grounding electrode conductor that is exposed to physical damage must be protected by one of the following means: firstly, rigid metal conduit; secondly, intermediate metal conduit; thirdly, rigid non-metallic conduit; fourthly, electrical metallic tubing; fifthly, cable armor; or sixthly, other approved means. The type of protection required will depend on the specific application and the degree of physical damage to which the grounding electrode conductor is exposed. In some cases, it may be permissible to use Sealtight, which is a flexible metallic conduit, to protect a grounding electrode conductor. However, Sealtight is not considered to be as robust as rigid metal conduit or other types of approved protection, and it may not be suitable for use in areas where the grounding electrode conductor is subject to severe physical damage. The NEC also contains specific requirements for the installation of ground rods. Section 250.53 G states that ground rods must be installed so that at least 8 feet or 2.44 meters of the grounding electrode is in contact with the soil. This requirement is intended to ensure that the ground rod provides a low resistance path to ground. The NEC also requires that ground rods be driven into the earth vertically unless rock bottom is encountered. If rock bottom is encountered, the ground rod may be buried in a trench that is at least 30 inches or 762 millimeters deep. The top of the ground rod must be flush with or below ground level, unless it is protected from physical damage. In addition to the requirements for ground rods, the NEC also contains requirements for other types of grounding electrodes, such as ground plates and concrete encased electrodes. These requirements are intended to ensure that all grounding electrodes provide a low resistance path to ground. The National Electrical Code emphasizes the importance of proper grounding and bonding techniques to minimize electrical hazards and ensure the safety of electrical systems. Grounding refers to creating an intentional low impedance path from electrical equipment to earth. Bonding involves connecting non-current carrying metal parts to create an electrically conductive path. These practices are crucial for the following reasons: firstly, personnel safety; secondly, equipment protection; and thirdly, minimizing fire hazards. Let's discuss personnel safety. Proper grounding and bonding help prevent electric shock by providing a low impedance path for fault current to flow back to the source. This path allows overcurrent protection devices like circuit breakers or fuses to quickly trip and to energize the circuit during a fault condition, reducing the risk of electrical shock to individuals who may come into contact with the energized equipment. Now let's delve into equipment protection. Grounding and bonding protect electrical equipment from damage due to voltage surges, transient voltages, and other electrical disturbances. By providing a low impedance path to ground, these surges can be safely diverted away from sensitive electronic components, preventing equipment malfunction or failure. Also, it's worth mentioning minimizing fire hazards. Fault currents flowing through unintended paths can generate excessive heat, which can ignite nearby combustible materials and cause a fire. Grounding and bonding help prevent this by providing a controlled path for fault current, reducing the risk of arcing, sparking, and overheating. There are various methods and techniques used for grounding and bonding in electrical systems. Firstly, equipment grounding conductors, or EGs, are used to connect non-current carrying metal parts of electrical equipment to the grounding system. EGs provide a low impedance path for fault current and help ensure that overcurrent protection devices will operate properly. Secondly, bonding jumpers are used to connect different metal parts of an electrical system together, creating an electrically conductive path. Bonding jumpers are commonly used to bond metal conduits, enclosures, and other metallic components. Thirdly, grounding electrodes such as ground rods, ground plates, and concrete encased electrodes are used to establish a connection to earth. Grounding electrodes provide a reference point for the electrical system and help stabilize voltage levels. Fourthly, surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges and transient. SPD diverts surge current to ground, preventing it from damaging sensitive electronic components. The National Electrical Code provides detailed requirements for grounding and bonding in electrical systems. These requirements cover various aspects, including the size and type of grounding conductors, the installation of grounding electrodes, and the bonding of metal parts. Following the NEC requirements is essential for ensuring the safety and effectiveness of electrical systems. One of the things that the NEC governs is the grounding electrode conductor, or GEC. It connects the service equipment or separately derived system to the grounding electrode. The size of the grounding electrode conductor is determined by the size of the service entrance conductors or the derived phase conductors. The NEC provides tables that specify the minimum size of the GEC based on the size of the service conductors. For example, Table 250.66 is used to determine the minimum size of the GEC for AC systems. Another important component is the equipment grounding conductor, or EG. It connects the non-current carrying metal parts of electrical equipment to the grounding system at the service or separately derived system. The EGC provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to operate. The size of the equipment grounding conductor is determined by the rating of the overcurrent protection device protecting the circuit. Table 250.122 in the NEC provides the minimum size of the EGC based on the rating of the overcurrent protection device. The ground ring is a continuous conductor that encircles a building or structure and is buried directly in the earth. It is used as a grounding electrode to provide a low impedance ground path. The NEC requires the ground rings be at least 20 feet or 6.1 meters in length and be buried at a depth of at least 2.5 feet or 762 millimeters. A concrete encased electrode, often called a U for ground, is a grounding electrode that is encased in concrete. It is typically used in new construction where the concrete foundation can serve as the grounding electrode. The NEC requires that concrete encased electrode be at least 20 feet or 6.1 meters in length and be encased in at least 2 inches or 50.8 millimeters of concrete. The connection of the grounding electrode conductor to the grounding electrode must be made using approved methods such as exothermic welding, listed pressure connectors, or listed clamps. The connection must be accessible for inspection and testing unless it is buried in concrete or otherwise made inaccessible. The National Electrical Code provides specific requirements for grounding and bonding in special locations, such as hazardous locations, healthcare facilities, and agricultural buildings. These requirements are in addition to the general grounding and bonding requirements and are intended to address the specific hazards present in these locations. Hazardous locations are areas where flammable gases, vapors, or dusts may be present. Grounding and bonding in hazardous locations is essential to prevent the accumulation of static electricity, which could ignite flammable substances. Healthcare facilities have sensitive electronic equipment that requires a reliable grounding system to prevent electrical noise and interference. The NEC provides specific requirements for grounding and bonding in healthcare facilities to ensure the safety of patients and staff. Agricultural buildings, such as barns and poultry houses, often have corrosive environments that can damage electrical equipment. The NEC provides specific requirements for grounding and bonding in agricultural buildings to protect equipment from corrosion and ensure the safety of livestock. Proper grounding and bonding are essential for electrical safety and equipment protection. The National Electrical Code provides detailed requirements for grounding and bonding in electrical systems. Following these requirements is essential for minimizing electrical hazards and ensuring the reliable operation of electrical equipment. There are specific differences between grounding and bonding. Grounding refers to the connection of electrical equipment to the earth. Bonding refers to the connection of non-current carrying metal parts of an electrical system to create an electrically conductive path. The purpose of grounding is to provide a low-impedance path for fault current to return to the source. The purpose of bonding is to create an electrically conductive path that will ensure that all metal parts of an electrical system are at the same electrical potential. The grounding electrode conductor, or GEC, connects the service equipment or separately derived system to the grounding electrode. The equipment grounding conductor, or EC, connects the non-current carrying metal parts of electrical equipment to the grounding system at the service or separately derived system. Improper grounding and bonding can create electrical hazards, such as electric shock and fire. Following the NEC requirements for grounding and bonding is essential for electrical safety and equipment protection. Grounding electrode systems are required to achieve a low resistance path to earth. This low resistance helps to ensure that fault currents will flow quickly and reliably back to the source, allowing overcurrent protection devices to operate and clear the fault. The NEC specifies a maximum resistance of 25 ohms for grounding electrode systems. If the resistance exceeds 25 ohms, an additional grounding electrode is required. Ground testing is performed to measure the resistance of the grounding electrode system. Ground testing is typically performed using a 3-point fall of potential test. This test involves driving 2 auxiliary ground rods into the earth and measuring the voltage drop between the grounding electrode and each of the auxiliary ground rods. The resistance of the grounding electrode system can then be calculated using Ohm's law. Ground testing should be performed periodically to ensure that the grounding electrode system is still effective. The frequency of ground testing will depend on the specific application and the environment in which the grounding electrode system is installed. Corrosion can degrade grounding electrodes and connections over time, increasing the resistance of the grounding system. Regular inspection and maintenance of grounding systems is essential to ensure their continued effectiveness. Grounding connections should be checked for tightness and corrosion. Grounding electrodes should be inspected for damage and corrosion. Any damaged or corroded component should be replaced immediately. The NEC provides specific requirements for the maintenance of grounding systems. Following these requirements is essential for electrical safety and equipment protection. Effective grounding and bonding are vital for electrical safety and the reliable operation of electrical systems. The National Electrical Code provides detailed requirements for grounding and bonding, and adherence to these requirements is crucial for minimizing electrical hazards and ensuring the proper functioning of electrical equipment.